Although the idea of civilization as a global geosystem might not pop up in your mind first thing in the morning, we'll attempt to make a case for it here today. This opening image was shot in Bethel, New York in 1969. This is Woodstock. The stage is located right down here. You can visit this today. There's a performing arts center that uses this field. The performing arts center is over here. There's a museum, which I don't recommend. It's terrible. But anyway, about 500,000 people showed up to this concert event after tickets were advertised. Now, they expected about 50,000 people or so. They lined up some major international acts, and the fence came down, the crowd came in, they stopped trying to get tickets off of people, and it became the socio-economic phenomena that we know about to this day. The first big concert. Again, about 500,000 people showed up in this little town in upstate New York. So what does that have to do with the global geosystem? Well, there are a lot of people now. The population is immense. Human population has been rising at an incredible rate, and the use of resources is also rising at an incredible rate. It's the balancing of resource usage versus environmental protection that we find particularly challenging. How much can we get at what cost? We're always weighing the pros and cons, the cost-benefit balance. It remains to be seen if we could use our resources in a sustainable way to continue to develop as a species and yet maintain some semblance of the world before we messed it up. So we'll talk about growth and impact of civilization on the geosystem. We'll talk about fossil fuel resources. How much is in the ground? How much can we get out of the ground? What's it going to cost us? Alternative energy resources. What are other ways we could obtain the power, the energy that we need to live our lazy, easy lives that differ from traditional ways of obtaining energy, principally fossil fuels? And at the end, we'll talk about our energy future. What is likely to happen in the future? And in this case, it's a particularly near future. Civilization itself exists at the thin interface between the climate, plate tectonic, and geodynamic systems. We're intimately involved with each of these. We experience climate change. We experience weather on a daily basis. We experience the good and bad associated with plate tectonics. Particular climates are derived because of the position on the Earth's surface of plates. The interaction of those plates may make for a good environment for us, or may make for a particularly hazardous environment for us. Proximity to earthquake zones and volcanoes, for instance. And then the geodynamic systems, things such as the Earth's magnetic field that protects us and invariably will fail us at some point. Now, since the Industrial Revolution in particular, human civilization has profoundly altered the planet, in some cases irreparably. We'll take a look at that. What have we done as a species to the Earth, not for the Earth? So looking at population growth, about 10,000 years ago, it's estimated that there were 100 million people on Earth. By 5,000 years ago, we doubled that to 200 million. 700 years ago, we hit 400 million. And by 1800, we hit 1 billion. Didn't take long to hit 4 billion. Took even less time to hit 7 billion. And we're expected to hit 8 billion by the end of the decade. Now here we can see population growth graphically. Again, starting about 10,000 years ago with 100 million people. We see what looks like a fairly steady rise. This is because we don't have any data, any good data. We start seeing perturbations here. These are generally disastrous events like pandemics that knock down the population. In some cases, it's climate related. When climate takes a downturn, we often see crop yields fail. We see animal production fail. We see starvation, we see civil disorder, unrest, warfare. Everything in human society collapses when humans really want something badly. And that's going to continue to get worse as we go into the future. As an example of our interaction, civilization as a geosystem, I mean, listen to this noise outside of my house right now. What is that? As some examples of human changes to the Earth, dams and reservoirs now trap 40% of all river sediment. This is sediment that's important for farming. It's important for bringing nutrients downstream. Rivers are also important for bringing nutrients upstream. they actually flow in the opposite direction. And that's something that we learned just recently about the Pacific Northwest. The salmon are very, very important to forest health. We didn't know that until we stopped the salmon from getting into the forest. Humans move more rock and soil than all natural processes. As a species, we're doing more erosive work than the natural world. We've managed to clear out 1/3 of all forests, get those trees out of the way. We've damaged the ozone layer with coolants, the chlorofluorocarbons. And we've pumped up CO2 levels by about 50% since the Industrial Revolution, since about 1850. We now are looking into renewable energy resources. This would be energy that supplies us with power to fuel machines, to drive, to heat, to cool. These include biomass, such as wood burning, switchgrass, things like that, and non-renewable energy sources, such as fossil fuels, oil, gas, and coal. Now, technically they are renewable, but on the 200 million year time scale, that kind of thing. It's not going to help us in the near future, these non-renewable energy sources. Now, U.S. energy consumption has been dominated by the burning of wood, coal, and oil, the 3 cheapest, most easily obtainable sources of energy, at least for the time being. Our coal usage is now declining, and we're seeing a decrease in petroleum usage as well. Alternatively, natural gas usage is up, and this is because of some new techniques that are used to get this natural gas much more cheaply. Nuclear energy has kind of leveled off. We had our love affair in the 60s, 70s, and the 80s, and then we got some scares, and now we're not so enthusiastic about it. Wood is actually increasing in usage, some of this being renewable forest. Hydroelectric power fluctuates, hasn't really increased substantially since probably the 1970s. What we do see a major change in is solar, wind, and geothermal energy and other biomass. This would include ethanol from corn and ethanol from switchgrass, things like that. We can see that the use of wood increased from the creation of the United States until about 1870, 1875 or so. And this leveling off and ultimately the decline in the use of wood is accompanied by the increase in the use of coal. Starting around 1850 in the United States and in Europe, coal became the predominant fuel of choice, predominantly used to generate steam, which turned steam engines and powered the Industrial Revolution in both Europe and the US. This coal continued to rise until the rise of petroleum in the early part of the 20th century. So as petroleum and gas became more common, cheaper, more useful, coal began to decline. And when we noticed how significant the pollution coal was generating was to the atmosphere of the world, we began to decrease the use of coal. It's on the rise again, mostly in developing countries, but just recently it started to take a downturn. So even in developing countries, the use of coal has a limited future. Natural gas and petroleum are getting cheaper to produce again, and as we'll see in a few minutes, it might be the end of them. They're at the end of their rope. So when we talk about fossil fuels, we discuss reserves that are known, we discuss reserves that are unrecoverable but suspected, and things that we would expect to exist but haven't found yet, if that makes sense. So with an increasing certainty of existence in this direction to the left, we have sources that have been discovered, deposits that are known and recoverable today. These are what we call reserves. We also have deposits that are known but not recoverable today. We know that the fuel is there, we just can't recover it economically at this point. And then we have undiscovered resources, things that are probably there. Every indication suggests that they should be there. We just haven't found them yet. And important to all of these categories is the feasibility of economic recovery. You can have a lot of stuff, but if you can't get to it, it doesn't matter. You can have a whole bunch of really nice cars somewhere, but if you can't get there, it doesn't matter that you have them. Same thing with fossil fuel. You can have a lot of it, but if you can't get to it, it doesn't count. When we look back in time in some more detail here, we can see that after 1850, we have the rise of the fossil fuel economy. This is a combination of coal, oil, and gas. The vast majority of our energy, even today, falls into those categories. This again began after around 1850 and describes the ride of the Industrial Revolution in the United States, as well as most of the rest of the world. What you'll notice towards the modern, around 1970 or so, nuclear energy became much more significant. Also notice that hydropower, although it had been increasing until about 1980 or so, it's starting to wane now. We're discovering some things about hydroelectricity that aren't particularly favorable to wanting to continue to use that energy source. Biomass is increasing. This is the use of biological materials as fuel. And we'll see that wind and solar are rising, some more rapidly than others, but rising nonetheless. So there's a transition underway. In the next 20 to 50 years, we're going to see a major transition from using fossil fuels to using renewables. We can see a bit of a blip here that starts about 10 to 15 years ago, where oil and natural gas are on the rise. And they're on the rise because they're much cheaper to get, and they're cheaper to get because of the technique we're using to get them, one of which is fracking. Now, they've gotten cheap enough that we're producing more than we need at this point. So for the first time ever, we've generated more fuel than we're consuming, and that has subsequently caused fuel prices to crash. And along with it, the Canadian dollar. Renewables, on the other hand, are on their way up. Nuclear is leveling off. It probably won't become significantly more important in the future. Renewables, however, will gradually take over the fossil fuel industry. This is the first oil well that was ever drilled anywhere in the world, drilled in Titusville, Pennsylvania. It's probably about 5 or maybe 10 years ago. I asked a question in class. I said, $2 to anyone that can tell me where the first oil well was drilled. And somebody knew exactly where it was. They knew the county in Pennsylvania, the township. They knew the distance from the little towns in the area. And I said, I'm impressed. Nobody knows that it's Titusville, Pennsylvania. How did you know this? And he said, oh, well, while you were talking, I Googled it. So I really don't deserve the $2. And I said, no, I'll give you $2 because you're really good at Googling things really quickly without me noticing. We need to characterize our consumption. Traditionally, it's done by using what are called British thermal units. These are units of heat or units of energy. And in this case, these are going to be converted to what we're going to call a quad. 1 quad is equal to 10 to the 15th British thermal units. That is a lot of British thermal units. The US in 2015 consumed 100 quads of energy. Globally, the same year, the world used 536 quads. So the US used 1/5 of the world's energy. US consumption by person is about 4 times the average of the world. So Americans use a lot more energy than any other group of people around the world. Now, when we break this down into consumption, we see that solar is equivalent to about 0.8 quads, nuclear about 10 times that, 8.4 quads, hydroelectric holding more or less steady at 2.8 quads, wind increasing. Right now it's about 2.4 quads. Biomass is kind of rising and falling with political winds, about 5 quads. Natural gas, a big player, 28 quads. Coal, another big player, 14 quads. And crude oil, the biggest and the baddest, at 36 quads. Ultimately, this is going to generate energy that we can use, known as useful energy. 31 quads of useful energy will be generated. About 66.6 quads, 2/3 of the energy that's used, is wasted. That's something we can work on. We're generating a lot of waste at the same time we're using this energy as well. In terms of carbon dioxide emissions from fossil fuel burning were equivalent to 1,453 megatons of carbon. Enormous amount of carbon going into the atmosphere as CO2 every year from the US alone. Now, when I first saw this figure, I thought, what the heck are they doing? This OECD here, Organization of Economic Cooperation and Development, is a weird mixture of a wide variety of countries. So it has nothing to do with the regions like these other categories, which baffles me in a way. So it includes North America, which would be the US, Canada, Mexico. It includes Chile, Colombia. It includes Estonia, Luxembourg. Again, anyway. So what this, I believe, is trying to indicate here is there's been relatively little change, slow growth amongst these countries, this wide smattering of countries. Africa, not much change. Central and South America, a slight increase as we see in the other categories, except for Asia, which is showing a huge increase in the amount of energy consumption. And this would include Russia, India, China, and all the other Southeastern Asian countries. This is going to have an impact on the Earth's atmosphere. And that impact on the Earth's atmosphere is going to affect us living in the Earth's atmosphere. So the global carbon flux from energy production has resulted in an enormous increase in the natural rate of carbon transfer. So we're putting an enormous amount of carbon dioxide into the atmosphere as a byproduct of the use of all this fossil fuel. And it's resulted in what we call a carbon economy. Carbon drives the energy which drives the economic systems of the world. Importantly, carbon dioxide is a greenhouse gas, which means it's very effective at absorbing outgoing long-wave radiation, infrared radiation that comes from the black body of the Earth that strikes the CO2, excites those molecules, causes them to vibrate and spin at a higher rate, and that means they get warmer, heat the atmosphere from below. These fossil fuel resources include, as we mentioned just previously, resources that have been discovered and reserves that remain in the Earth. We know they're there. We can get to them without too much trouble, and we can recover that energy economically. Here we see the global estimates of fossil fuel reserves, believed to be 53,000 quads. Of that, the majority is coal, and just behind coal is heavy oil and tar sands. Both of these are heavy polluters, heavy emitters of CO2 and lots of other things. Crude oil, slightly cleaner, significant. Natural gas, slightly cleaner than crude oil, also significant. And then we have tight oil and gas, a little bit more difficult to get to. Coal, where does it come from? How does it form? Why is it there? The most rudimentary discussion of the formation of coal would list it as a biological sediment of accumulated plant material. Dead plants packed together in an oxygen-poor environment, compressed, kept wet usually, it's going to turn into peat. Chemical reactions also serve to change it, and as this plant material is compressed and heated, it can be converted into coal, driving away the water, driving away the other volatiles. Here we have a couple images from Ireland, some work we did in Headford Bog outside of Galway. This is a cross-section of peat. This is the peat surface. Amanda Dolbert sinking to her demise into the peat. You have to watch where you're walking or this will happen to you. Your legs disappear beneath you. So cutting into this using machinery, so these boggy, swampy plants here produce this organic matter. And you can see that, I think you can see, it's a dark brown water, kind of like dark tea or coffee color. This is from the tannic acid that is present in the peat bog. And it's a preservative. If you throw a body into a bog, it will be perfectly preserved for 2,500 years. And you can Google bog bodies or bog mummies, things like that, and see lots of examples of people that have been thrown into these bogs over the last few thousand years. So this plant material accumulates in this anoxic water and gradually gets compressed. Ultimately, it is dug up. In this case, it was dug up by machines. Traditionally, it's dug up by hand with a weird triangular shaped tool. Looks like a modified hoe. And in Ireland, it's called foot in the turf. So you go out to foot the turf to generate these little brick-sized logs. These are about the size of a regular red brick, and they're used like firewood. So this is a cheap form of fuel, and you'll see it used all over Ireland. There's actually a peat board, a group of people that decides which peat gets harvested and which peat does not get harvested. And often there are archaeological treasures discovered during this harvesting process. So this is how coal starts out. Coal begins as plant material. It accumulates in anoxic water, gets compressed. If it gets significantly compressed, it may turn into a form of coal called lignite. This is cheap coal, not particularly energy rich compared to other types of coal, but better than the peat that people in Ireland burn in their stoves. Bituminous coal is buried further, so it's more compressed, and it is converting into a more energy-rich form. If it's buried and then heated significantly, but not too significantly, it can form anthracite. This is the grade A coal. This is hard, it's black, it's shiny, looks like a rock, burns like really good coal. So this is what you really want. Also important is where this environment forms. If this is salt water, then there's going to be sulfate in the coal. That means when you burn it, you're releasing sulfur dioxide. If it's fresh water, you don't have that sulfur problem. So ideally, you want your coal to form in a freshwater environment. It's compressed and it's heated to a couple hundred degrees for 10 or 20 million years maybe, and you get a nice anthracite coal as a result, end product.